Okay, guys. So last time we finished chapter number 4, and today we are going to start the new chapter, that is chapter 5, some discrete probability distribution. There are two chapters, chapter 5 and chapter 6. In chapter 5, we are going to see just discrete probability distribution, and in chapter 6, we are going to see the continuous probability distribution. So chapter 5 is completely based on the discrete, means we are going to see. Here we are going to see the binomial distribution and the hypergeometric distribution and the relationship between binomial and hypergeometric distribution. Already, I think you guys have gone through the binomial distribution. So that's why very quickly, I just would like to go over the binomial distribution. And then after, we are going to do the main article of this chapter. There is article 5.3, hypergeometric distribution, and then 5.4 and 5.5 like this. So let me just give you a brief idea about the binomial and multinomial distribution. And once we are done with this one, then after we will switch over to hypergeometric distribution. We are going to see the mean and variance of a binomial distribution, that is usually denoted by B and bracket X semicolon N and P, where mean is usually given by mu equal to NP and variance, that is sigma square equal to NPQ. And we are going to see the same thing for the hypergeometric distribution, and that is the mean is the same, but the variance is slightly different than the binomial distribution. We are going to say about the relationship to the binomial distribution, relationship of hypergeometric distribution to the binomial distribution, and we'll be solving some examples. So that today's lesson plan, that is based on this article 5.2 and 3. So introduction, that is okay, already I gave it to you. The binomial and multinomial distribution, mainly you can see over here, whenever we have this type of things at that time, suppose we have an experiment often consists of repeated trials, each with two possible outcomes that may be labeled success or failure. So please keep in mind this thing, that experiment often consists of the repeated trials. Repeated trials are there, right? Repeated trials are there. That means you know this thing, that repeated means it is independent events. So repeated trials are independent. So please keep this thing in mind. So binomial distribution is mainly for the independent trials, and the hypergeometric distribution, that is for the dependent trials. That means in which we are not going to see the repetition but non-repeated. I mean, suppose we have a deck of cards, and suppose we take the one card, and that whatever it may be, then we don't count that, we don't put that card back, we don't replace that card, we just keep that card outside. So that is the hypergeometric distribution. But in binomial, yes, repetition is there, so you have to put this card back, and then you can go for the next trial. So every trial is independent. Okay, so an experiment often consists of repeated trials, each with two possible outcomes that may be labeled success or failure. Here we are going to discuss about the success rate and the failure. Success and failure, that is the most important thing. Success and failure, the most obvious application deal with the testing of items as they come off an assembly line. So suppose you have an assembly line and you are testing the item. Suppose you have bulbs, light bulbs, right? And you are testing this bulb. So this testing of bulbs, suppose they are defective or not defective. In some of the examples, what will happen there, suppose the bulbs are non-defective. That means we have a lots of material, loss of material as well as the money, because that's not of any use. So once the bulb is defective, right, it will go, it goes to the dustbin, to the trace. And that's why every time we don't use the binomial distribution, in that particular case, one has to use the hypergeometric distribution, because the replacement is not possible. So there are fundamental real life questions in which really says us, say us how to deal with or why to use the hypergeometric distribution. This is one of them. So testing items as they come off an assembly line, where each trial may indicate a defective or the non-defective item, we may choose to define either outcome as a success. The process is referring as a Bernoulli. When an outcome is a success, the process is referring as the Bernoulli process. Now, outcome is success, total probability is 1. Suppose success we denote by P, and total probability is 1. So non-success means failure can be written as P plus Q equal to 1 always, because success and non-success is always equal to 1, right? So if you're looking for success means P, and non-success means it is 1 minus P. So non-success I would like to denote by Q. So always again P plus Q equal to 1. So Q is nothing but 1 minus P. P is success, and if you remove those success rate from 1, that means you are going to get the failure rates. So P is success and Q means 1 minus P is the failure. So this process that is called the Bernoulli process, and each trial that is called the Bernoulli trial. So please keep this thing in mind. There are 4 points one has to memorize, one has to keep in mind for this Bernoulli process. The first one is that experiment consists of repeated trials. I told you that each experiment is a repeated trial, and because it's a repeated trial, that means they are independent. So these repeated trials are independent. So they are one and the same. Actually, 1 and 4, they are correlated. Once you say it's a repeated trials, means they are independent. Each trial results in outcome. They may be classified as a success or failure. Once you have that one trial, suppose on a production line, suppose you pick one bulb and that bulb is non-defective, that means a success rate, right? So you can consider that one as a success. If it is defective, you can consider that one as a failure. So that's the reason, that's the meaning. The probability of success, now we denote this probability of success. You know that probability of success and failure, that is always probability cannot exceed 1, so it has to be equal to 1. Right? So probability of success, suppose success rate is 3 by 4, so naturally failure rate is 1 minus 3 by 4 is 1 by 4, like this. So I repeat, the experiment consists of repeated trials, means independent. Each repeated trial is independent. Each trial results in an outcome that may be classified in terms of success or failure, and the probability of the success we denote by P. So naturally the probability of failure is Q, P plus Q equal to 1. So please keep this thing in mind, and then after this I would like to go for what is the definition of a binomial distribution. The binomial distribution, as I told you, that is given by the Bernoulli trial, can result in a success with probability P, as I told you. The failure, that is 1 minus P, that is equal to Q. The probability distribution of the binomial distribution or binomial random variable X, the number of success in an independent trial is number of success in an independent trial. Please try to look at the language. What we are doing, binomial distribution gives us the number of success in an independent trial. Number of, how many n independent trials are there? Independent trials, n number of trials, success, probability of success, right? And out of this n independent trial, we have X, a random variable, right? Okay, and that is given by NCX. NCX, that means it is given in the form of the combination NCX, P to the power X, Q to the power N minus X. And these X are number of trials, so 0, 1, 2, 3, up to N, right? 0, 1, 2, 3, up to N. And suppose we take N equal to 3. I think it is better if I take the example, so probably that would be more better. And I would just like you to read this example 5.1, and then after we'll switch over to the whiteboard. The probability that a certain kind of component will survive a shock test is 3/4. Find the probability that exactly 2 of next 4 components tested survive. Next 4 components, 4 is your N, and out of this 4 you are testing just 2, that is your X. So you are testing your 2, that is your X. So you can write X, that is 2, N equal to 4, and your probability, success rate, probability of a certain kind of component will survive. Component will survive. Surviveness means successness. Please keep in mind this thing. So it's just a different language, but it is to be understood that we are talking about a success rate. So probability of a success, that is 3/4. So my P equal to 3/4. I can plug these values over here, right? And exactly 2. Look at over here. Exactly 2. That means you have to take X is equal to 2. X is equal to 2. X is just 2. Just 2. So just plug the value 2 and then use the combination definition and you will get the answer. So that's what we are going to do. So let me switch over to the whiteboard and I can go over these 2 things. And then after we can go for the next one. And why this binomial, that we will discuss later, but let me just go for stop sharing this one and let me go for my whiteboard. My whiteboard says that the Bernoulli trial can result in a success with probability P. So definition says that Bernoulli distribution, binomial distribution, binomial distribution, a Bernoulli trial can result in a success Bernoulli trial can result in a success with probability P and a failure with probability Q equal to 1 minus P. Always keep in mind this thing that P plus Q is equal to 1, always, because P plus 1 is equal to Q. Okay, then the probability distribution of the binomial random variable X, then the probability distribution of the binomial random variable X, the number of success in n independent trials, the number of success in n independent trials is given, let me take this one aside, set up professional audio in, okay, let me just close this part, okay. And trial is given by binomial, because this B stands for binomial, first word, and here it is X semicolon N and P, and that is equal to NCX and P to the power X and Q to the power N minus X, where X runs from 0, 1, 2, 3, dot, 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 up to N. Always keep in mind this thing that your X is less than N. Here we are going to use the combination formula NCR, that is equal to N factorial over N minus R factorial times R factorial. So please keep this thing in mind too. Suppose we have, as per example, suppose this is the definition. This is the definition. As per example, suppose I have N equal to 3 and P equal to 1/4, right? The probability distribution X can be written in the form of probability distribution, binomial distribution, N equal to 3 and this is 4. So that is equal to NCX, N equal to 3CX, and P is equal to 1/4. So 1/4 to the power X, and Q is equal to, P is equal to 1/4. Now look at here, P is equal to 1/4 and Q is equal to 1 minus P. So 1 minus P is equal to 1 minus 1/4, that is equal to 3/4. So Q is equal to 3/4 and 3/4 to the power N minus N is equal to 3 and 3 minus X, N minus X. Same here, suppose you have X is equal to 0, 1, 2, 3, something like this. Here also 0, 1, 2, 3, right? X is equal to 0, 1, 2, and 3, because if you compare over here, X is equal to 0, 1, 2, 3. Suppose I take X is equal to 0, I'm going to get B 0, semicolon 3 and 1/4. That is equal to 3C0, and here it is 1/4. X is equal to 0 and 3/4. X is equal to 0, so it is 3. 3C0, 3 factorial divided by 3 minus 0 is 3 factorial, so it is simply 1, and 0 factorial is 1. Any integer to the power 0, that is again 1, and here it is 9 divided by 4, 4s are 16, 4s are 64, so 9 by 64. So your answer for this one is 9 by 64. Same way, suppose I have X is equal to 1. In that case, my binomial distribution 1 and 3 and 1/4, so that is equal to, here it is 3C1 and here it is 1/4 to the power 1 and 3/4 to the power 3 minus 1, that is equal to 2. 3c1 is 3 factorial over 3 minus 2 factorial, that is equal to 3. And here it is 1/4, and here it is square. 3 square is 9, and here it is 16. So that is equal to 9 3s are 27 divided by 64, like this. Suppose I take n is equal to 2. In that case, I'm going to get 2 and 3 and 4. So out of 3 components, if you are selecting 2, okay, and the success rate is 1/4, the binomial distribution is given by 3c2 and 1/4 and square, and here it is 3/4, and 3 minus 2 is equal to 1. That is equal to 3c2, that is equal to 3 factorial divided by 3 minus 2 is 1 factorial and 2 factorial. And here it is 1/4, that is equal to 1/16, and I'm going to get, here it is 3/4. So that is equal to 3 factorial. So it can be written as 3 into 2 factorial. So 2 will get cancelled out. So again, you're going to get 3 divided by 16 and 3/4. So that is equal to 9 divided by 64, like this. Same way I can go for x is equal to 3. So b, I'm sorry. So here it is b, 3, and then after 3 and 1/4. Again, you can plug the values. That's 3c3, 3c3. That is equal to, again, 3 factorial over 3 minus 0 factorial and 3, that is equal to 1, and 1/4 and cube, and here it is 3/4 to the power 3 minus 3 is 0. Here it is 1, here it is 1 cube, so 1 over 64, and here it is simply 1. So it is 1 over 64. So this way you can find for different x, 0, 1, 2, and 3. Right, guys? 0, 1, 2, and 3. Example 5.1, as I told you, it says that example, let me take 5.1. Just now we read this example. The probability that a certain kind of component will survive a shock test, means P is equal to 3/4 is given to you. Find the probability that exactly 2 of next 4, exactly 2 means x is equal to 2 and n is equal to 4. Next 4 component tested survive. That means binomial distribution of 2, and here it is 4, and success rate is 3/4. Success rate is 3/4. That is equal to NCX, so that is equal to 4C2, and probability is 3/4. 3/4 to the power x. X is equal to 2, and 1 minus 3/4. 1 minus 3/4. That is my Q to the power, yes, to the power, what is the definition? 3, here it was, n minus x. N is equal to 4 and minus x is equal to 2. That is equal to 4c2, and here it is 9 by 16, and here it is 1/4. So 1/4 to the power 2. That is equal to 4c2, that is equal to 4 factorial divided by 4 minus 2 is 2 factorial times 2 factorial. Here it is 9 by 16, and here it is 1 by 16, right? So this 2 factorial, 4 into 3 into 2 factorial, and this will get cancelled out. Here it is 2 2s are 4, so we are getting here 6, right? So that is equal to 9 multiplied by 6 divided by 16 square, 256. Right, guys, 256. So that is equal to 54 divided by 256. So that is equal to 27 divided by 128. So that is the find the probability that exactly, so if exactly 2 out of 4 components tested and they survive, in that case, the probability is 27 over 128. 27 means you're going to get some decimal, and that is the answer. So that's how you can solve the example. Again, let me just save this one in my folder. Okay, and then after, let me clear this one, and we can go for the book. So book says that, now, where does the name binomial came from? Actually, you know that whatever we have done over here, look at over here, Q plus P, A plus B to the power N, or whatever we are writing over here, that just look at over here, look at the definition, NCX P to the power X, Q to the power N minus X. If you all of us are well aware of the binomial expansion of 2 numbers. Suppose you have I mean to say two variables. Suppose you have x and y. So x plus y square, that is equal to x square plus 2xy plus y square, like this. So exactly same thing, this binomial expansion that is being developed based on the same part. So let me just let you know this thing too. So again, let me stop sharing this one and let me share my whiteboard, because I think the some of the things are not given in the book, but it is equally important for us to know the things. So binomial expansion says that binomial expansion says that suppose you have a plus b to the power 2 that is equal to, or I can say a plus b that is equal to a to the power 1 plus b to the power 1. Here a square plus 2ab plus b square. Suppose I have a plus b cube that is equal to a cube plus 3a square b plus 3ab square plus b cube, like this, and so on, so on. So finally, we are getting a plus b to the power n. This is the general form, generalization. Generalization. A plus b to the power n can be written in the form of a to the power n plus NC1. Actually, it is okay. I will like x a to the power n, then NC1 a to the power n minus 1 and introduce b. Then NC2 a to the power n minus 2 and b square. Reduce the power of a and increase the power of b gradually. Then NC3 a to the power n minus 3 and b cube. 3, 3, 3, 2, 2, 2, 1, 1, 1. So I can write over here NC0 if you want. Let me just rewrite this one nicely so that everyone can read this part. So I can write a plus b to the power n, that is equal to NC0 a to the power n and b to the power 0. Ultimately, NC0, that is nothing but just 1, because this is 1 and b to the power 0 is also 1. That's why we don't write. We simply write a to the power n. But actual formation is like this. Okay, then dot, dot, dot. Go ahead. If you go like this, you're going to get NCn and a to the power 0 and b to the power n. So the previous term is NCn minus 1 and a to the power 1 and b to the power n minus 1. Here, if you replace this, a is equal to suppose p and b is equal to suppose q. This p is your success rate, and q is nothing but the failure. So I can write the same thing in the form of p plus q to the power n, that is equal to NC0 p to the power n plus NC1 p to the power n minus 1 and q plus NC2 p to the power n minus 2 and q square dot, dot, dot. And finally, NCn, again, NCn is simply 1, no need to write, right? So, and here it is q to the power n. In your book, it is given q here and p here, but I think this is the right formation where p plus q is always equal to 1. Naturally, because p plus q is equal to 1, and if you write this one summation of b, binomial distribution x, we are selecting x out of number of choices and my success rate p. So this is always equal to 1 because this one equal to 1. So you can say that since p plus q equal to 1 implies that this one is equal to n, x runs from 0 to n, x is equal to 1, 2, 3 up to n. So that means the probability, sum of the probabilities is always equal to 1, that we know, right? Sum of the probabilities that is always equal to 1. Then after, once you talk about this one, so naturally it's this x is nothing but the random variable, is the random variable x. Because it's a random variable, so again we can talk about the mean, because we went over all these parts, right? So mean and the variance for the binomial distribution. So mean and the variance of a binomial distribution. So mean of the binomial distribution and variance of a binomial distribution. Mean of binomial distribution x NP and binomial distribution X and NP. Mean of the binomial distribution that is given by nu is equal to NP, and variance is given by sigma square is equal to NP and Q. Sigma square that is equal to NP and Q. NPQ. Right, guys? So just keep this thing in mind, and then after you can extend the binomial distribution to multinomial distribution, multinomial experiments, and the multinomial distribution too. So instead of just one x, we have now just one x over here. Look at here, just one x. We have now x1, x2, x3 up to xn. And we have the success rate for x1 is p1, x2 is p2, x3 is p3, like this, and n remains the same, and because they are the number of components, right, number of trials, okay, and remain the same. So if you extend the same part, so generalization of the binomial distribution, generalization of binomial distribution is given by, look at here, guys, for if a given trial can result in k outcomes, E1, E2, Ek, with the probabilities P1, P2, Pk. You can say like this. You can say k outcomes or n number of outcomes. Usually we denote some k. So suppose we have the P1, P2, P3, k outcomes with the probabilities P1, P2, P3, then the probability distribution of the random variable x. Okay, so given trial results in k outcomes. If a given trial results or can result in k outcomes, given trial can be result in small k outcomes, and that is given by E1, E2, E3 up to Ek. K outcomes, you can just keep this thing in mind with probability P1, P2 up to Pk. Then the probability distribution of the random variable, then the probability distribution of the random variable x1, x2 up to xk, x1, x2 up to xk, representing the number in all independent trials, in all independent trials, that is given by f of x1, x2 up to xk, then n, then p1, p2 up to pk, p1, p2 up to pk, and that is given by nc, not x, but now it is x1, x2 dot xk, x1, x2, xk, p1 to the power x1, p2 to the power x2, p3 to the power x3 dot pk to the power xk, pk to the power xk, with summation of xi I is equal to 1 to k, that is equal to n, and summation of pi I is equal to 1 to k, that must be probability cannot exceed 1, so that is equal to 1. So please keep this thing in mind. This is the multinomial distribution, but we are not going to use this one. This is just for your knowledge. So now I would like to switch over to our main article that is called the hypergeometric distribution. Whatever I taught you so far, that was just the revision, whatever you have gone through in your past, in your previous grades, maybe in 12th grade or 11th grade or something like that, but you have gone through this thing, that is pretty much sure. Okay, so now let's go first. Let me clear this one. And now I just gave the generalization just for your knowledge. Mainly we'll be dealing with only this part. We will be dealing with this portion. Okay, and binomial distribution. So mainly we are dealing with this part. This portion along with this portion. This and these two are important things for us. Okay. Let me clear this one now. And now I would like to go for the hypergeometric distribution. So now my article is hypergeometric distribution. Again, I'm telling you that binomial distribution, that is with replacement, dependent trials, hypergeometric distribution, that is without replacement, dependent trials. So please keep this thing in mind. The simplest way to view the distinction, I mean, it's a difference, right, between the binomial distribution and the hypergeometric distribution is to note that way of sampling is done, how the sampling is done in both ways, in both different distribution, binomial and hypergeometric. There's a basic necessity, there's a basic difference. The types of applications for the hypergeometrics are very similar to those of the binomial distribution. Types of application, just look at over here. Let me stop sharing this part. Let me share this one with you. We did this, all these parts, and now look at this one, guys. Yes. So if you read this one, you will come to know the simplest way to view the difference between binomial and the hypergeometric distribution is the way the sampling has been done. Sampling is done. The types of applications for the hypergeometric can very similar to those of the binomial distribution. So please keep this thing in mind too. We are interested in computing the probabilities for the number of observations that fall into a particular category. We are interested in computing the probabilities for the number of observations that fall into a particular category. But in the case of the binomial distribution, independence amongst trials is required. You know this thing. As a result, if the distribution is applied to the sampling from a lot of items, suppose deck of card or batch of production line or like this, the sampling must be done with replacement of each item after it is observed. On the other hand, the hypergeometric distribution does not require the independence, and it is based on sampling done without replacement. So that is the most important thing. Very frequently I've been telling you this thing, this difference. So that is, the item is destroyed because I told you that suppose you have the production line and you are testing the electric bulb, and suppose the success is failure rate. I mean to say it is defective. Defective means one, the bulb is not working. That means it will go to the trace. That means you have loss of money and the item. That means you cannot replace it back now. So there are some, I give you that example, right? So that is, the item is destroyed and hence cannot be replaced in that particular category in the sample space, in the sample. And thus the sampling without replacement is necessary in a practical purpose like this. And that is why we have to learn, we have to try to figure it out some way out to find the probability. And that is given by the hypergeometric distribution. That is given by the hypergeometric distribution. There are mainly two properties for the hypergeometric distribution. So in general, we can say that we are interested in a probability of selecting n successes from k items labeled success and n-1 failures from n-k items labeled, capital N-k items labeled. That is given over here. Just look at over here. I just would like to let you know this part. In general, we are interested in the probability of selecting n successes, x successes, sorry, from the k items. Right? So naturally you have x successes. Now you know this thing that x success, that means you are taking x out of your small n. So total n minus x. And k success means total number of components are n. Out of this n, k successes are there. So n minus k is a failure, right? Like this. So we are interested in the probability of selecting x successes from the k items and the k items labeled success and n-x failure. X successes. So naturally, total number components are n, sample space, sample elements, and out of these X, out of these X we are selecting. So naturally, success, so n minus X is a failure from n minus k items, labeled failure when a random sample size n is selected from n items. So n is a capital N is a very large group. Out of this very large group, we are selecting just n number of items. Just like suppose in United States, we want to go for the election poll. I mean to say that the prediction, right? The forecast of the election, that who is going to win the election, Republican or the Democrats. At that time, it is not possible to go over and ask every citizen who are eligible to vote or who is eligible to vote. Just ask to that particular guy in person and and take his opinion. That's not possible. It's very time consuming and it's not possible always. So that's why we are going to form some group, and we are going to take the, suppose we consider one of the institution, George Mason University in Washington, DC. Then we go to Atlanta and we take over there, suppose one of the universities over there at Atlanta. And like this, right? Then we go to, suppose, New Jersey, Rutgers University, and we ask from this university, these are our X, these are our N, number of universities, and we just try to collect the X from this N. Now we are not going to, suppose we have 20,000 or 30,000 students in one university. We are not going to ask all these 30,000 students, but we can take, suppose, 50 students from the engineering section, 50 students from the science section, 50 students or 500 students from, or 100 students from natural and natural science section, natural arts section, like this. And then after we can ask them and try to collect all these data from different universities. So that is my capital N is the total population, total number of people staying over here in United States who are eligible to vote. Then after we made a partition of different universities, that is our N, small n, and this small n, of course, is a subset of capital N. Out of this small n, we are testing some of the students. We are asking from the students, that is our choice, and that is my X. So always keep this thing in mind like this. So that's how it works. So the properties for the hypergeometric experiment distribution is the random sample size N is selected without replacement, most important thing, from capital N items, right? N is selected from capital N items. Of the N items, K may be classified as a success. So naturally, N minus X or N minus K that is classified as a failure, because K is success out of this N, capital N. So N minus K, that is the failure rate. There's the failure rate. The number X of successes of hypergeometric experiment is called the hypergeometric random variable. So whatever X now we are going to learn, we are going to use, that is nothing but the random variable, but that is in terms of the hypergeometric random variable. Previously, we have used that one as the binomial random variable or Bernoulli random variable. So now it is the hypergeometric random variable. According to the probability distribution of the hypergeometric variable is called the hypergeometric distribution. Hypergeometric distribution. So please, the hypergeometric distribution in acceptance sampling. So acceptance sampling, where lots of materials or parts are sampled in order to determine whether or not the entire lot is accepted. So now I would like to go for the definition for hypergeometric distribution and its mean and the variance. Definition of hypergeometric distribution that is given like this. The probability distribution of the hypergeometric random variable X, the number of success in a random sample size N selected from capital N items, of which K are labeled as success, so naturally N minus K is failure, as I explained to you. So hypergeometric, because this H stands for hypergeometry, H, okay, first word of hypergeometry is H, and that's why we denote this one by H, X, N, and K. This is the pattern of writing, X, N, and K. That is given by KCX, your success rate. Previously it was P, now it is K. KCX, then failure rate is N minus K and N minus X, total number of population N, and sample is N. So you can see over here, my X is always less than K, N minus X is less than capital N minus K, and small n is less than capital N. Just keep in mind this thing, whenever you write combination, at that time, your upper number must be higher than the lower one. And we are taking the maximum of 0, and n minus k is less than x is less than minimum of n and k, right? We will discuss this in later. Okay. Suppose now I would like to consider the example. Just read this example, and then after we will be doing we will be solving this one. It says that a lot of 40 components each are deemed acceptable if they contain 3 or more defectives. A lot of 40 components. 40 components, your capital N is 40. Just keep in mind this thing. Lot of 40 components. There are no more than 40. So just total population, total numbers, 40. Total number of items, 40. 40 components each are deemed unacceptable if they contain 3 or more defectives. The procedure for sampling a lot is to select 5 components at random and to reject the lot if the defective is found. Look at over here. It says that the procedure, 40 components are there, deemed unacceptable if they contain 3 or more defectives, right? 40 components are there and 3 or more defectives. Now, K is your success rate. Here, success rate means always, it's not always positive. It is something like this, what you are looking for. You are looking here in this particular example, you are looking for the component deemed unacceptable if 3 or more defectives. So success rate is if you are getting 3 or more defectives means it is not acceptable. Not acceptable is your success rates. Don't say that defectives. No, not acceptable. But in which case it is not acceptable? It is not acceptable when the lot contains 3 or more defectives, right? 3 or more defectives. So please keep this in mind, this thing that small k equal to 3 in this particular example. The procedure for sampling a lot is to select 5 components at random. Now, out of this 40, you are going to select 5 components at random, means my small n equal to 5, and to reject the lot if a defective is found. Okay, what is the probability that exactly 1 defective is found? Means my x is equal to 1. Exactly 1 defective is found in the sample if there are 3 defectives in the entire lot. That is my k, 3 defective in entire lot. So I am going to write this x is equal to 1 based on this example, my n equal to 40, my small n equal to, you can see over here, that is equal to 5, and k is my success rate, that is equal to 3. So if you use this one, let me again share my whiteboard so that you can come to know these things. So let me go for the whiteboard. In hypergeometric distribution, let me write it down, the formula also for you. So h of x, total population, and number of samples, and k, the success rate, right? K is the success rate. And x is nothing but the random variable x. This is nothing but, yes, random variable x, the number of success in a random sample size. N is the sample size. Selected from n items, number of items. This is number of, or total number of items. Total number of items, sample size, and the success rate. Success rate, right? And labeled as success. Naturally, k is success. So this implies that my total n minus k is equal to failure. And this definition is given by kcx. Here it is n minus k and c n minus x divided by nc and divided by nc. And just please keep this thing in mind. And my x runs from 0, 1, 2, it goes up to small n, total number of samples. Right, guys? In this particular, this is my definition. This is the definition. In this particular example, 5.9, in example 5.9, we have 40. So H is equal to exactly 1. We are selecting n equal to 14, small n equal to 5, and rate of success equal to 3. This can be written as K is equal to 3C1. Then after capital, this is my X and small n and K. Capital N minus K, that is equal to 40 minus 3, that is equal to 37. And small n minus X, that is equal to 5 minus 1, that is equal to 4, divided by capital N, that is equal to 40C5. This can be written as 3 factorial, 3 minus 1 factorial, that is equal to 2 factorial. So 3 factorial is simply 3. And here it is 37 factorial divided by 37 minus 4. 33 factorial and 4 factorial divided by 40 factorial and 40 factorial and 40 minus 5, that is 35 factorial and 5 factorial. This 40 factorial can be written as 40 into 39 into 38 into 37 into 36 into 35 factorial. This 35 and 35 will get cancelled out. Here it is 5 into 4 into 3 into 2 into 1. So this 5, 4 and 4. So here you're going to get 10 and something like this. Here 37 can be written as 37 into 36 into 35 into 34 into 33 factorial. This 33 will get cancelled out. That means I'm going to get 3 times. Here it is 4 is nothing but 4 into 3 into 2. So here it is 4 and here it is 9. So that is equal to 37 times 9 times 35 times 34. So I can write here 17 divided by, here we are getting simply 3, right? Here 30 and 3, so 3 3s are 9, so I can write 3 over here. 3 3s are 9. Okay, so everything is gone. And here I'm getting, yes please, if you look at this one, here it is 12 and here it is 6, and I think that's it. So 10 multiplied by 10 multiplied by 39 multiplied by 38 multiplied by 37 multiplied by 6. Use your calculator, whatever the number you are getting, that must be your answer. Here you are getting 3.003011. That means almost 30%. Almost, we say that if you follow this plan, this plan is not desirable since it detects a bad lot, 3 defectives only about 30% of the time. So this plan, if you apply this plan, that out of 40 you choose 5, and if you apply this plan, that means you are getting 3 defectives. With 3 defectives only about 30% of the time you are getting this one. So this plan is not desirable. This plan is not acceptable. Okay, and then after I would like to go for the mean and the variance for the hypergeometric distribution H, X, N, K, H, X, capital N, and K, and K. So nu is equal to NP. That was the mean for the binomial distribution. But here my P is nothing but K over N. Here my P is nothing but K over N. So please keep this thing in mind. My P is equal to K over N. So that means it is N K divided by N, and K divided by N. And my variance sigma square is given by capital N minus N over N minus 1 times N times 1 minus K over N, 1 minus K over N. Right, guys, 1 minus K over N. Here it was, just keep this thing in mind. So N minus N, N minus 1, and this one. Okay. In binomial distribution, it was, so mean remains the same, but the variance is different in the hypergeometric distribution. In binomial and hypergeometric means mean always remains the same, P is equal to this one. But in binomial distribution, we have sigma square is equal to NPK. We have sigma square is equal to, I think, NPQ, sorry, NP and Q. Right here, that is not the case. So N is there and P is, as I told you, that is K over N, P is equal to K over N, and Q is equal to, yes, please see, P is equal to K over N. This is my P. So N minus K over N minus 1, right? So that is my Q, something like this. So you can match like this, but they differ in variance. So variance is different. So please keep this thing in mind, that this is the mean for the hypergeometric distribution. This is the variance for the hypergeometric distribution. And now I would like to go for the next example. My next example says that is the example number 5.10. Example number 5.10. It says that, please listen to me carefully. Let us now reinvestigate the previous example, some other example. I think that is okay. You don't want it. Okay. I think that is fine. It says that suppose you have age and 3, and here it is 100 and 10 and 12. So if you have okay, let me just go through this one. So let me share this screen with you. Stop sharing. So in the folder, now stop sharing and let's go to the book. Look at here, guys. It says that let us now, example 5.10, let us now reinvestigate example 3.4 on page 83. I don't know what it says, page 83, 3.4, long back, right? Example 3.4 on page 83 that says that statisticians use sampling plan to either accept or reject batches or lots of materials. Suppose one of this sampling plan involves sampling independently 10 items from the lot of 100 items in which 12 are defective. 12 are defective, 100 items capital N, lot of sampling independently 10 items, means small n equal to 10. Let X be a random variable defined as a number of items found defective in the sample of 10. In this case, the random variable takes the values, okay, 0, 1, 2, 3, up to 10. That is the example. We continue with the same example over here. It says that, let's now reinvestigate the same example. I just buried that example for you. The purpose of this example was to illustrate the notion of a random variable and a corresponding sample space. In the example, we have a lot of 100 items, of which 12 are defective, as I told you. What is the probability that in a sample of 10, 3 are defectives? Okay, that means my X is equal to 3. My X is equal to 3, X is equal to 3, capital N equal to 100, small n equal to 10, and small n equal to 10, and my rate of success k equal to 12. So just plug this value, right? And plug this value. So let me just go back and let me share my screen with you. Okay, so, and then after you can evaluate, you can find this thing very easily. So that is equal to, here it is 12C3, right? Because KCX, and you have n minus, so n minus k, that is equal to 100 minus 12, k is 12, that is equal to 88. And here it is small n minus x. Small n is 10 minus x, 10 minus x, that is equal to 10 minus 3, that is equal to 7, total 110. Again, if you use the combination formula, you're going to get some answer. That's the probability. And same way you can find the mean and the variance of the random variable of example 5.9 given to you. Okay, 5.9. So in example 5 here it is example 5.11, and we are referring to example 5.9 in which we are given n equal to 40 and we were given n equal to 5, k equal to 3. These are the numbers provided to us, and we are looking for the mean. So mean is given by nu is equal to n k over n. N k over n. N is equal to 5, k is equal to 3, and that is equal to 40. That is equal to 3 by 8. And 3 by 8 is equal to 0.375. So that is your mean. And you can find the variance. The variance given by sigma square is equal to, sigma square is capital N minus n. Just use this formula. Capital N minus n is given by 40 minus 5 divided by capital N 40 minus 1. That is equal to 39. Then n is equal to 5 is given to you in the problem. Look at here. And n equal to 5, and then after 1 minus k over n. So 1 minus k equal to 3 and capital N equal to 40. If you open this bracket and try to solve this one, you're going to get that is equal to sigma square. And if you apply Sebezius polynomial, that means we are going to get nu plus or minus 2 sigma. That is a Sebezius polynomial. Nu plus or minus 2 sigma. Now nu is equal to 0.375, and this sigma you are getting over here, that is equal to 0.3113. So plus 2 times 0.3113 and minus. If you write plus and minus, you're going to get two numbers. The first number, because here it is, if you multiply it by 2 and then subtract from here, you're going to get 0.741, negative 0.741. And the another number you are going to get, that is equal to 1.491. 1.491, right? If you use this formula, this is due to Sebezius polynomial. Okay, so taking the sum square roots of this one, and actually I think this sigma, this is a sigma square. So sigma is equal to square root of sigma square, right? And that is equal to square root of this number. That will be probably, I think, 0.558. So I have to use that number over here, 0.558, 0.558. And you are getting these two numbers, I'm sorry. Okay, so 0.558, and that means that lies between the required interval. This will provide us the interval. So required interval 0.741 and 1.491. This is the required interval. Required interval, that is this one. And Sebezius theorem states that the number of defectives obtained when 5 components are selected at random from a lot of 40 components, of which 3 are defective, has a probability of at least 3/4 of falling, between the range of 0.741 and 1.491. 1.491. That is at least 3/4 of the item, the 5 components include fewer than 2 defectives. That is the meaning. I repeat, I said that once you take nu plus or minus 2 sigma, you are getting two numbers. By Sebezius theorem, we say that the number of defectives obtained when 5 components are selected at the random from a lot of 40 components, of which 3 are defective, has a probability of at least 3/4 of falling between negative 0.741 to 1.491. 1.491. Right, guys? 1.491. And that is at least 3/4 of the time the 5 components include fewer than 2 defectives. 5 components, because n equal to 5, they are getting fewer than 5 components include fewer than two defectives. Okay, guys, so that's how it works. So in the folder, let me clear this one. And now the relationship between the binomial distribution and the hypergeometric distribution. Again, let me share my book. It's really, sorry. It's really good to understand, I'm going to say, to refer this part. You can see here, there is an interesting relationship between the hypergeometric and the binomial distribution, as one might expect. If n is small compared to capital N, the nature of capital N items changes very little in each draw. For a binomial distribution, so the binomial distribution can be used to approximate the hypergeometric distribution when n is really, really small. Guys, please keep this in mind. Capital is extremely large number, and if you are taking very small number for n, your sample space, very small number, in that case, the binomial distribution is approximated by the hypergeometric distribution. So the question arises that how small my small n would be compared to my capital N. So it says that small n by capital N must be less than 0.05. Small n over capital N, that is equal to, that must be less than or equal to 0.05. That is if this is the case, in that case, what will happen, that binomial distribution, you can see binomial distribution can be used to approximate the hypergeometric distribution. If this is the case, if small n divided by capital N is less than 0.05, in that case, the binomial distribution can be used to approximate the hypergeometric distribution, right? And thus the quantity k over n plays a role of the binomial parameter p, right? Now we are comparing our mean and the variance of binomial distribution and hypergeometric distributions. So NP equal to this one, K over N, that remains the same as I told you, but there is a difference over here in the variance. The mean and the variance then come from the formula this one. Comparing this to formula of this one, we see that the mean is same, but the variance differs by the factor is n minus n over n minus 1. N minus n over n minus 1, which is negligible when n is small enough relative to your capital N. Right, this n minus, which was the portion in, we say what, hypergeometric variance of hypergeometric distribution, which doesn't appear over here because this portion is really, really negligible. So just please keep this thing in mind. And now I would like to go for some of the examples from the exercise problem. Rest of the things you can read by your own, and let me start with the exercise problems. Just give me a minute and we can start with the exercise problems. These are just the expansions of the hypergeometric distribution, and which I'm not interested. See, expansion of multivariable hypergeometric distribution. Just like your previous case, x1 to xk, they are the random variables, and a1, a2, ak, they are your rate of success over here. And total number n, and out of n, that is a population, n is the success rate. Summation of xi must be equal to total samples, and summation of ai, success rates, must be equal to your n. So a1 to ak, n is the item of the partitions into k cells. A1 to ak will be a1, a2, ak elements respectively. Then the probability distribution for the random variable that is given in this form, that is the hypergeometric. And this is the example. That's fine, but I would like to go for a few of the examples. Just try to, this is the generalization. That's fine. Once you understood the part for small x, capital N, small n, and k, I think that is enough for us. One can generalize this one very easily, so it's not required. And let's go for the examples. Just a minute. So let's go for a few of the examples, and then after we will stop So my first example says that which example we want to solve. Number of examples are there. I think it is better if we can go over example number. I would say 5.31. Yes, 5.31 says that what it say? What it says? A random committee of size 3 is selected from 4 doctors and 2 nurses. It's total 6. And committee of size 3, random committee of size 3 is selected from 4 doctors and 2 nurses. Okay, write a formula for the probability distribution of the random variable X representing the number of doctors on the committee. How many doctors are there? 4 doctors, right? Total 6, but 4 doctors in the committee and 4 doctors, right? And you are forming the committee of 3. You are forming the committee of 3. So please keep this in mind. So I would like to keep my X as a random variable and total 4 plus 2 equal to 6. My total population N equal to capital N equal to 6. Out of this 6, what is my small n? My small n, that is my committee, right? We are forming the committee of 3 members. So my small n equal to 3. And the rate of success, because we are selecting doctors. How many doctors are there? 4 doctors. So rate of success is K is equal to 4. So that's how I'm going to take over here. So let me again stop sharing this one and let me go to the whiteboard. So example number 5.31. 5.31, it says that hypergeometric distribution X, N, and K, and that is equal to age X, 6, 3, right? 4 nurses and because 4 plus 2 and 4 doctors and 2 nurses, total population N equal to 6. And then small n, that is the committee is formed, sample space of 3 people, and success rate says that all of them must be a doctor, right? Representing the number of doctors in the committee. So this representing number of doctors in the committee. So I can now just use my formula NCK, N minus K, and small n minus X, and here capital NC. And this is the formula for this one. So let me write that is equal to, help me guys, that is equal to 4CX, and here it is 2 and 3 minus X, right? Because here N equal to 6 and K equal to 4. So 6 minus 4 equal to 2. And here it is 6 and here it is 3. 6C3. So that is, and my X is nothing but X in this case is equal to committee is formed. So 1, 2, and 3. Don't say X is equal to 0 over here, guys. Please be smart because you cannot form the committee with 0 member, right? It has to be at least 1 member in the committee. So X is equal to 0, 1, 2, and 3. Okay. So what? That is equal to, yes, please. Now it says that find probability of, so you can write like this, and then after you can find probability of 2 is less than or equal to X is less than or equal to 3. Equality is there. That means I can write age. Let me put X is equal to 2, X is equal to 2, and then X equal to 3. If you take X equal to 2, then semicolon 6, 3, 4 minus age equal to 3, 6, 3, 4. That is equal to, here you can see X is equal to 2. So 4C2, 2C1, and here it is 6C3 minus 4C3 and 2C0 and 6C3. And that is equal to 4C2, that is equal to 4 factorial divided by 4 factorial divided by 2 factorial times 2 factorial, right? So 4 into 3 into 2 factorial will get cancelled out. Here is 2, so here it is 6. You are getting 6 over here. 2C1, that is equal to 2, right? 2 factorial, 2 minus 1 is 1 factorial and 1, so it is 2 factorial. 6C3. 6C3 can be written as 6 into 5, or sorry, my bad. It is 6 factorial divided by 6 minus 3 is 3 factorial and 3 factorial. 6 into 5 into 4 into 3 factorial. 3 factorial will get cancelled out. 3 into 2, 6, and 6, so it is 5 4s are 20. So here you're going to get 20. So that is my first part. Minus, here I'm going to write 6C3, that it will again be 20. And here we're going to get 6, here, right? So 4C3. 4C3, that is equal to 4 factorial over 4 minus 3, that is equal to 1 factorial, and 3 factorial. It is simply 4. So I'm going to get 4. I'm going to get 4. Then 2C0, that is equal to 2. 2 factorial, 2 minus 0 is 2 factorial. So it is 2C0 is 1, right? 2 factorial, and 2 minus 0 equal to 2 factorial, and 0 factorial is 1. So it is 1. Okay, then 6C3, already I wrote it down. If you simplify this one, you are going to get what? Here it is 20, and for 6 to the 12 minus 4, that is equal to 8. So that is equal to, yes, please, 4 by 10 or something like this. That must be your answer. Am I right, guys? Let me just double check this one. So here it is 6 into 5 into 4 into 3 factorial divided by 3 factorial times 3 factorial, right? 6 minus 3 is 3 factorial. 3 factorial, 3 factorial will get, and 3 factorial is equal to this one. 5 4s are 20. I think I'm good. 5 4s are 20. Okay. Okay. And here it is. So here 4, and here it is 1, right? Okay. So 6 to the 12 and minus. So that is equal to something 4 by 20 or 4 by 10, something like this. So that must be your answer. So please, guys, please keep this thing in mind. Okay, let's go for one more example. That is example number. Let me save this one in the folder, and let me clear this drawing, and let me stop sharing this one, and let me again share my book. So 5.33 example says that, very important example. I like this type of examples. If 7 cards are dealt from an ordinary deck of 52 playing cards, what is the probability that exactly 2 of them will be the face card? Exactly 2 of them will be the face card. That means I can write exactly 2 means x equal to 2. Total number of cards, that is equal to 52. So capital N equal to 52. If 7 cards are dealt, means sample space is 7, so small n equal to 7, right? Dealt with the ordinary deck of 52 cards, exactly 2 cards will be the face cards. How many face cards are there in the deck? Yes, face cards. That means how many face cards? King, 4 king, 4 queen, 4 jacks. These 12 are the face cards. So my k equal to 12. So please, guys, keep this thing in mind, k equal to 12. So let me plug these values in my, and then after my second question, at least one of them will be a queen. At least one of them will be a queen, right? So we are first going to find non-queen parts, and then after we'll reduce that one, we'll subtract that one from the probability 1. I can do that example for you. So if you have 5 point example 5.33, it says that a part, let me take, and it says that exactly 2 of them will be the face card. So hypergeometric distribution, exactly 2 of them will be the face card. Total number of cards 52. 7 is a sample space. Face card. Face cards k equal to 12. So that is equal to, I can write 12C2, and then after I can write 40C5 divided by 52C7. And if you open this one, you're going to get, I did that thing that is equal to something 12C2 and like this 0.3246. 3246. And B part says that hypergeometric distribution, it says that at least one of them will be a queen. Now, one of them will be a queen means out of this one, at least one of them will be a queen. So for queen, 1 minus one of them, right, will be a queen. How many queens are there? So 48. total cards without queen. Out of 52 cards in a selection of 7. If no queens means 48, right? And if I subtract from 1, that will give me the direct answer. So you don't have to apply the hypergeometric distribution directly. If you apply this one, you're going to get the answer. So 1 minus 48 factorial divided by 48 minus 7, that is equal to 41 factorial, and 7 factorial whole divided by 52 factorial divided by 52 minus 7, that is equal to 45 factorial times 7 factorial. And just cancel the common terms, and whatever you're getting, that is the answer. Then I would like to go for example number 5 suppose 35. So let me again stop sharing and share my book. If we share the book, 5.35 is like this. Nice example again. It's okay. 5.35, 36, and we'll stop. We are going to take these two examples together, 5.35 and 36. First, 35. A company is interested in evaluating its current inspection procedure for shipment of 50 identical items. The procedure is to take a sample of 5 and pass the shipment of no more than 2 are found to be defective. No more than 2 are found to be defective. That means 1 defective, that is okay, but not more than 1. 0 defective, fine. What proportion of shipments with 20% defectives will be accepted? What proportion of, see, procedure is to take a sample of 5, n equal to 5, and pass the shipment if no more than 2 found to be defective. No more than 2 found to be defective. Okay, and success rate is, you can see what proportion shipment with 20% of defectives will be accepted. 20% of 50 identical items. 20% of 50, that is equal to, right? Am I right? 20% of 50, that is equal to 10. So my K equal to 10 over here. So please keep this thing in mind. And let me find this one. So that is simple. So 5.35 says that, example 5.35 says that my P, probability of the random variable X less than or equal to 2, that is equal to, here you have to be a little bit careful. You are not asking just your age and then X and then your N equal to 50 and your N equal to 50 and X equal to 5 and K is equal to 10. This K is equal to 10. It's not like this, because this K is nothing but 20% of 50, that is equal to 10, and that is my K, which I have used over here. But this is nothing but K less than, that means you have to go for the summation, because here X runs from X is equal to 0, 1, and 2. 0 defective allowed. So you have to start with X equal to 0 or 1 or 2, but less than or equal to or 2, right? So if you use like this, you are going to get that is equal to, yes, please. If you use this one in the formula, you will be getting, let me write it down directly. I think you can finish this example by your own because I gave you everything. So that is summation. You can first take X is equal to 0, then X equal to 1 and X equal to 2. And every time you have to use the hypergeometric distribution. And finally, you will be getting one answer that is 0.9517. That's 9517. That's what the answer I have. Right, guys? So just plug this X equal to 0 over here, X equal to 0, or I can write it down for you if you want. Okay. So X is equal to 0. That means here it is age 0, 50, 5, and 10. Then age 1, 50, 5, and 10. Then plus age 2, 50, 5, and 10. And use hypergeometric distribution for all these 3 terms. And finally, you will be getting this one as the answer. This is the answer. Now I would like to go for my next example, last example, I would say. Let me stop sharing this one. And again, I would like to go for the book. Example 5.36. A manufacturing company uses an acceptance scheme on items from a production line before they are shipped. The plan is a 2-stage one. Boxes of 25 items are readied. Boxes of 25 items are readied for shipment, and a sample of 3 items is tested for defectives. Sample of 3 items is tested for defectives. Okay, if any defectives are found, the entire box is sent back to 100% screening if any defective is found. If no defective is found, no defectives are found, the box is shipped. What is the probability that a box containing 3 defectives will be shipped? Okay, 3 defectives means my success rate here is 3. That means I can write each. Read this example carefully, guys. It says that the manufacturing company uses an acceptance scheme on items from a production line before they are shipped. The plan is to stage 1 boxes of 25. That means my capital N equal to 25 are readied for shipment, and a sample of 3 items, that means my n equal to small n equal to 3 out of 25, are tested for the defectives. If the defective rates are, right, 100%, means all 3 items are defective, then my k equal to 100. K equal to, if no defectives are found, the box is shipped. What is the probability that a box containing 3 items will be shipped? That means no defective is found, right? That means x is equal to 0. That means I can write like this. And my second part is, what is the probability that box containing only 1 defective will be sent back to the screening? Will be sent back to the screening. So, what is the probability that a box containing 3 defectives will be shipped? Means x is equal to 0. And what is the probability that a box containing only 1 defect, means x is equal to 1? So that's what we are going to do now. So my last example that says that example number 5.36, and it says that h, x, n, and nk hypergeometric distribution. For a part, I have probability of x is equal to 0. X is equal to 0, and that is equal to h of 0, and then n25, then 3, and here it is 3. So that is equal to 3c0, and then 25 C3, right? 25 minus x, that is 25 C3 and 25 C3. Am I right? 25 C3 and 536. Just let me see. 25 C3. 25 C3, and so that is equal to, I think, no. The definition for this one is nothing but KCX, right? So this is your, let me just verify this thing, guys. So it says that KCX, so K is equal to 3x is equal to 0. So KCX is equal to 3C0. This is K, and this is my x, KCX. And then after I have capital N minus K, that is, it has to be 22 over here, my bad. Has to be 22 over here. 25 minus 3, that is equal to 22. 22, and it says that n minus x. So n minus x, small n minus x is 0. Okay, and then when that sounds good. So it is 25 over here. It has to be 22 over here. My pen is dropped down. So if you solve this one, you're going to get one number. You're going to get one number, something, I don't know. And the B part is the probability of x less than, sorry, x is equal to 1, right? X is equal to 1. That is equal to 1, 25, 3, and 3. So that is equal to 3C1 now, and 22C3 divided by 25C3. Am I right, guys? 22C, not 3, but I think it is 3 minus, that is equal to 2, because it is n minus x, right? N minus x. And here it is NCN. So everything is good now. Yeah. So you're going to get one number over here too. Maybe 3 over 25, and I got it 77 over 115. So that is your answer. That is your answer. So that is the end of article 5.3. And next time we are going to start the negative binomial and geometric distribution. negative binomial distribution and geometric distribution. That's what we are going to see next time. And then after one article will be left out, and that is based on the geometric, and I think simultaneously we can go for the Poisson's distribution and the Poisson process too. So maybe when next time we can finish this chapter, but 2 more articles we are going to learn from this chapter. Okay, guys, so I think this is more than enough for today's class, and just keep working with this one, and you will have the complete idea about this thing. So let me just stop sharing my screen. Let me save this file so that it will be useful for us to upload this one on the YouTube, so that whenever you want it, you can have the same lecture just like one-to-one teaching on YouTube. So please try to refer this thing, try to take the advantage of this one. Okay, guys, and now let me stop sharing and let me stop my recording too.